Let's pick up with example 14 here, more complicated trig function here. So, pick the more complicated piece on this, alright? We have the integral of sine squared of 3x cosine of 3x. Notice there's two trig functions in this integral. There's a sine and a cosine. So this is a scenario where we don't want to pick necessarily the argument. We want to have to pick one of the trig functions so it eliminates the other one. Pick the more complicated trig function. Sine squared is more complicated than cosine. So we're going to choose u to be sine of 3x. Now when we take the derivative of u, we're going to get the derivative of sine of 3x. That's a chain rule. Okay, so it's going to be the derivative of sine is cosine, so it'll be cosine of 3x times the derivative of the argument is 3. Okay, so make sure we're paying close attention there. So du is going to be cosine of 3x times 3 dx. So we have to rewrite that. The cosine of 3x dx will cancel, but we have to divide both sides of 3 by 3. So we're going to have du divided by 3 equals cosine of 3x dx. Now we can do direct substitution for the cosine of 3x dx as du over 3 and sine of 3x as u. So when we rewrite this integral, we're going to get the integral of u squared times du over 3. Factor out that 1/3. So we're going to have 1/3 the integral of u squared du, which ends up being 1/3 times the antiderivative of u squared, which is u cubed over 3 plus c. Now we substitute our original u back in for the u in this scenario, which is sine of 3x. So we end up getting 1/3 sine cubed of 3x over 3 plus c. We can also factor out that 1/3 that's underneath the sine cubed of 3x. So we end up getting 1/9 times sine cubed of 3x plus c. Alright, let's do example 15. We have 3 times 3x minus 1 to the 4th. So we're going to let u equals 3x minus 1. So du will be just 3. That's a perfect replacement. Du is 3 dx. So when we replace this and rewrite this integral, everything's going to work out nicely. So we're going to end up with u to the 4th du. When we take the antiderivative of u to the 4th, we get u to the 5th over 5 plus c. We replace the u back in, so we're going to have 3x minus 1 in for the u. So we'll have 3x minus 1 to the 5th over 5 plus c. And we just keep kind of moving on here. Let's take a look at this one. We're going to multiply two binomials. Choose the more complicated of the binomials to be your u. So we have the integral of the quantity of 2x plus 1 times the quantity of x squared plus x dx. U is going to be the more complicated one, so we're going to choose u to be x squared plus x. Therefore, when we take the derivative of u with respect to x, du is going to be 2x plus 1 dx. That's a perfect replacement for us. Notice that there is a 2x plus 1 dx next to the integrand, so we don't have to do anything special. We can now rewrite the integral, take the antiderivative, and replace u. So, we end up with the integral of u du. The antiderivative of u is u squared over 2 plus c. Now we replace the value of x squared plus x in for u. So our final answer is x squared plus x quantity squared divided by 2 plus c. Example 17. We have the integral of 3x squared times the square root of x cubed minus 2 dx. Choose the most complicated piece for u to be. It's what's underneath the radical. So u is going to equal x cubed minus 2. Taking the derivative of u with respect to x, du gives us 3x squared dx. That's going to be a perfect replacement when we rewrite this integral. So rewriting the integral, we have the integral of the square root of u du. So u's substituting back in, and du replaces the 3x squared dx. We rewrite the integral, since it's a radical, let's write the integral as the integral of u to the 1/2 du. We're going to take the antiderivative of that, which we have done multiple times. It ends up being 2/3 u to the 3/2 plus c, and then we substitute the value we chose for u of x cubed minus 2 back in for u. I really think we're getting the hang of this. I think it's more or less the figuring out the u piece, so I'm going to kind of go through these a little bit quicker. If we look at example 18, it's pretty obvious. The more complicated piece is the 1 minus 2x squared to be u. Then when we take du, we get negative 4x dx. That's a perfect replacement. You should be able to write that integral here as the integrand of du over u squared. Rewrite that over u squared as u to the minus 2 so we can bring it back up top. Take the antiderivative, which is u to the minus 1 over negative 1 plus c. We just plug u back in here. So minus 1 minus 2x squared to the negative 1. And remember, we can bring that back down to the denominator so that it has a positive exponent. We don't leave answers with negative exponents, which leaves us with negative 1 over 1 minus 2x squared plus c. Another trig function here, very similar to the previous one that we did. Alright, choose the more complicated one. This is not where we need u to be the argument, but we need u to be the a trig function that makes it work. Alright, so if we let u be cosine of x, du equals negative sine x dx. Notice that's not quite a perfect replacement. It's a good replacement for sine of x dx, but there's a negative in front. So we need to make sure that we replace du over negative 1 with sine x dx. We got to divide both sides by that negative 1. So now when we rewrite the integral here, we're going to get the integral of u squared times du over negative 1. That negative we can pull out in front of the integrand. So it's going to be negative the integral of u squared du. Now we treat everything the same way. We take the antiderivative of u squared, which is u cubed over 3 plus c, but we got to make sure that that negative stays in front. Then we replace u with cosine of x, so our final answer ends up being negative the quantity of cosine cubed x over 3 plus c. Next we're going to get into the change of variables. I'll start a new video for you guys on that one.